Before continuing with part 2 of the impedance analyzer for the analog discovery, I received another reply from Attila at Digilant having to do with the previous issue, that is using script with the spectrum analyzer in Waveforms. And you can find this at Home, if you look right up here at the top, Home, Digilant Technical Forums, Scopes and Instruments using script with spectrum on AD2. And the reason that I'm sort of excited about this is it appears that Attila has provided, I haven't tried this yet, but it looks like what he has provided, and I'll go down to the message. It's a little bit down here. And this was posted 6 hours ago, but what it shows is a window. This is the basically the Waveforms script window. And you see there is a script at the bottom which basically does an analysis of total harmonic distortion, and it provides an example. And he's even provided the code to do all of this. In other words, what this is doing is it is sweeping from a start frequency to a stop frequency and doing THD analysis at each of the points in between. So it prints the reference frequency. I'll zoom in a little bit more here. And the way this is written is in standard, this is the way that scripts are written in the analog discovery. If you're familiar with JavaScript, well, this will be easy for you. He defines a function called doTHD, and he uses one waveform generator, and then he uses the spectrum analyzer, which is, of course, basically one of the scope channels with fast Fourier transform. And then he measures the frequency, stops the wavegen, prints the data, and plots it. So what he has basically done is showed how to use the script, how to write a script. Now, there is also another individual, and I hope he won't mind me mentioning this, who has I don't know if I'm pronouncing this right, Abza, who says, I'm working on a Python script to at least do some of the basic automation of THD analysis across the 20 hertz to 20 kilohertz spectrum. So these are two slightly different approaches, but they accomplish the same thing. Now, I haven't tried any of this, and the model or script that Attila has provided, I will be trying probably in the next day or so. But for right now, I just wanted to let people know that if you haven't checked out the Analog Discovery Forum recently with regard to this THD issue, and you're looking to replace the audio analyzer suite with an automated THD analyzer using the Analog Discovery, well, you might want to go over here and check it out. It looks like if we're not there, we're awfully close. Well, anyway, now let's move on and do part 2 of that impedance analyzer. After I published the part 1 on the impedance analyzer for the Analog Discovery 2, Craig Hollabaugh sent me, I hope I'm pronouncing that right, Craig, he sent me a comment to my video pointing out that he had also done a video on the same subject, and so I went over and looked at that. Now, Craig has sent me a number of good comments over the last few weeks or months on the Analog Discovery and some other things. So, but I had not subscribed to his channel, and that was a mistake. I should have. So I have now done that, so that I won't wind up missing these kinds of things again, at least from him. But after I went over and looked at this video, I realized that there were a couple of things that he was doing that would help others, and of course it's always great to have a different perspective. So here is the his YouTube address, or it's just his name, and the video that is shown here, he calls it the Valve Studio, and he's done some others that I have also found interesting. Some of those are on the Analog Discovery as well. So I suggest, or actually highly recommend, that if you're watching these videos on the Impedance Analyzer, or you're just interested in audio in general, but especially using the Analog Discovery with audio, then check out Craig's website. I think it's, or his YouTube channel. I think it's, he's got some great stuff on there. And I apologize to Craig for missing this video initially. I've been pretty tied up on a number of things, and frankly I haven't been able to cruise YouTube for about 2 weeks or 3 weeks. But great site, try it, and I think you'll learn a lot. And as I learned after years in electronics research, the more people you have on something, and the more motivated they are, the faster things developments multiply. So keep up the good work, Craig, and I hope that a lot of viewers will find your channel and some of the excellent videos there. I hope you'll pardon all of the digressions, but I thought that it was important to get some of those other messages and videos out. Where I am going to go now is doing some experiments on transformers, similar to the experiments I did using an LCR meter in a previous video. Before I do that, for those of you that may not have watched that video or need a little bit of a review on transformer theory, here are some basic transformer equations that I think you might find useful. And I realize a lot of you already know this. If you define the number of turns in the secondary as n sub s and the number of turns in the primary as n sub p, then the ratio of the voltage in the secondary to the voltage in the primary is the same. So for example, suppose that ns is 10 times np, then that means that es is 10 times ep. So if you put 1 volt on the primary, you'll get 10 volts on the secondary if it's a 10-to-1 transformer. The current, on the other hand, is exactly the inverse. In other words, the current in the primary will be 1/10 the current in the secondary if I just said that backwards. The ratio of the current in the primary to the current in the secondary, which notice this is upside down from this, is in the same ratio as the number of turns in the secondary to the number of turns in the primary. Notice primary here, primary is on the top there. Also, another fact that is very useful is in impedance transformation. If you have, say, a 10-to-1, or let's use a 16-to-1, it's easier to do in my head, ratio between the turns in the secondary to the turns in the primary, then you will have a 4-to-1 ratio between the impedance in the secondary and the impedance in the primary. The reason is, of course, 16, you take the square root of that, is 4. So these are some rules or some formulas that are very useful, and I may be referring to some of those as we go along. Next thing that I wanted to point out is, if you recall, when we were doing impedance measurements on the transformer, and I'll go back up and refer to this diagram first. You may, I've referred several times to the fact that because the secondary is open, this acts just like an inductor. Well, that's not actually true. It turns out that when you have a magnetically coupled secondary, even if you leave it open, it does have an effect on the primary. And one of the reasons is, this is a kind of actually simplified version of what goes on in a transformer. Notice that in addition to just the primary and secondary windings, there is also capacitance, both in the primary and the secondary. Those capacitances produce resonant frequencies, and the primary resonance and the secondary resonance can be quite different. Another thing is, there is capacity between the primary windings and the secondary windings. It's called mutual capacitance. And so just as there is mutual inductance between these two, that is coupling, magnetic coupling from this one to this one, and reverse from this one back to this one, there is also capacitive coupling. There is a quantity often called leakage reactance, which is the reactance of the or the equivalent reactance of the losses in the transformer. So, for example, if you put 1 watt into the primary, you might only get 9/10 of a watt in the secondary, and the difference is usually modeled with a leakage inductance. And if you haven't watched my earlier video on that, that was one of the things I was talking about, was how you can measure this actually using an impedance meter. Finally, there is a resistance that is in series with the primary and in series with the secondary, which just represents the resistance of the wire that's being used. Often this is very fine wire and at many turns, so the resistance, the DC resistance, can often be relatively large. I'm not going to talk more about this model at this time, except we will note that when we start measuring things, for example, if you leave the secondary open, what you actually have is a tuned secondary. That is, this capacitance and this inductance will tune to some frequency. And at that frequency, there will be a tremendous amount of energy absorbed from the primary. So if you apply a signal here and vary its frequency, you will find a point at which there is a big dip in the response. And that's because the energy is being absorbed in this parallel resonant circuit. There also is a point at which this primary will become a parallel resonant circuit, and once again there will be a dip. So there often are two dips, and you may recall we saw that in the characteristic of that transformer. The last thing that I want to mention is that transformers are made usually with laminated cores, and the reason that the cores are laminated is to cut down on what are called eddy currents. If you just use a solid core, the tendency is, of course, you induce the magnetic field that's in the primary induces not only current in the secondary, but also current in the core itself. And that current will travel around in circles here, and those are called eddy currents. And what they do in transformers, and those get worse as the frequency goes higher. So what they do is they separate the core into thin sheets. They make up layers like this. Well, usually this is called the E and this is called the I. And what they do is they lay down an E along with an I, and the next layer, the second layer, is the opposite way. The idea is that you allow magnetic fields to circulate in this, but you try to prevent electric signals, that is voltages or currents, from circulating in this material. Now, when you get to a high enough frequency, even this doesn't work, because then there are eddy currents right inside the core material itself. So that's one of the reasons why the transformers tend to drop off at high frequencies, is because of losses in the core. So the last thing that I want to mention, these last two pictures I actually took from the ARRL Handbook for Radio Communications. This is an excellent source of information if you are looking for some sort of general source of information on electronics. This is one of the best books that I know of. There are others like The Art of Electronics and so on, but in terms of real hands-on practical knowledge, the ARRL Handbook is, in my opinion, very good. So enough time wasted, let's get on to the experiments. So here you have the impedance analyzer with a display that you saw in part 1. And the thing I want to talk about for a second are these inverted peaks here. What is going on, and by the way, let me turn on impedance also. I think I explained earlier that one of these is the resistance and the other is the capacitance. And by the way, speaking of the resistance, just for a second, you may wonder, why isn't the resistance just a straight line? Well, the fact is that the resistance, because it includes eddy currents and other things that affect or are reflected as additional resistance, the actual resistance of a transformer, primary or secondary, over a frequency range is not a constant because of all of the parasitics. So you notice that the resistance goes up with frequency, then it goes down with frequency. That's because of the effect of capacitance. Then it goes back up with frequency again, and the inductive reactance, that is the X sub P, the primary inductance or impedance, goes across and then it drops way down, goes back up and goes way down again. These are because of the resonances in the primary and the secondary that we talked about. I'm going to turn on the impedance graph as well. In fact, let me, so you can see it a little better, turn off these two graphs. This is the actual impedance, and we'll be talking more about this because somebody asked a question about whether you can use a power transformer as an output transformer for a tube circuit, and the answer is, like most things in life, it depends. It depends on the turns ratio of the transformer, the core material, how the windings are put on it, and so on. And the short answer is yes, you can use it, but you may not get very good performance. So there is the actual impedance. This is the vector sum of the resistance and inductive reactance. So keep your eye on this. In fact, I'll turn off the others so that you can just see this. And what I'm going to do is now load the secondary with a 100 ohm resistor. And we'll rerun. And you notice now it's just a straight line. Let's turn on the other. So let me just leave it running here as I switch that 100 ohm resistor in and out of the circuit. and you see what it does to the, now remember, we're looking at the primary of the transformer. And what is happening is, by loading the secondary with a low resistance, 100 ohms in this case, we're effectively swamping those parasitics. And the primary now looks like a pretty well-behaved impedance. It goes up with frequency. And let's just look at just the impedance of the primary. And if we went and measured the secondary and looked in reverse, we'd find the same thing is true, that we would have some resonant points if we drove the secondary, because a transformer is relatively symmetric. But we would have to load the primary if we wanted to get rid of the effect of those parasitic resonances. And that is basically what happens in the output transformer of a tube circuit. Now, in a second, we'll move on and look at some things like that. But I wanted to point out that one of the things that in the later days of high fidelity tube amplifiers, a lot of attention was put into how to build a transformer, an output transformer especially, that would cover a wide frequency range and would also provide good efficiency, low parasitics, etc. And when transistors came along, because of their low output impedance, the need for these more expensive transformers went away because they used direct coupled outputs. And with the disappearance of the need, disappeared the research as well. So today, most transformers, except a few special military applications where there was additional research that was conducted later, sort of came to an end about 1970 or so, maybe 1975. And so we're really dealing with some pretty old technology here. So if you feel like you might be able to improve on modern day transformers, and certainly with the better tools and knowledge that we have today, and the better materials, better core materials, better wire and other things, it's likely that somebody can develop a better transformer today. And I know there are some people still working on it, but nowhere near the number that were working on these things back in the 50s and 60s. Before I leave this, I do want to point out why it's important to recognize that you have these kinds of characteristics. If you have watched any of my videos on feedback, especially feedback in hi-fi amplifiers, you will see that the problem, when you get up in the higher frequency range, now this is only 10 kilohertz right here. So this, actually both of these are within the frequency range of a good hi-fi amplifier. Most of them go out to around 100 kilohertz, which is where this, the right-hand edge of this is. And so these tremendous changes in impedance get reflected back through the feedback network into the input. And that's one of the reasons why that hi-fi tube amplifiers would often oscillate at higher frequencies. Sometimes, in this case, this one might oscillate around 15 kilohertz, where this resonant point is, or around 36 kilohertz, where this resonant point is. Now, better transformers, these resonances move out further and further, but they're still there. So let's take a look at an output transformer. I've changed the setup a little bit. What I've done is I've gone to the night signal tracer that you see in the background there, and I'll show you the schematic in a second, but I'm really only using this for its speaker and output transformer. Everything else is pretty much the same. You'll see in a minute, though, that when you switch from the power transformer to the output transformer, you do have to make a few changes in the system. But let's take a look first at the schematic of this signal tracer and get an idea of what we're working with here. There you see the output transformer, and the center tap and the two outside leads are brought out to binding posts on the front of the unit. And then there's a switch that allows you to insert the speaker or leave it disconnected. Now, for reasons of preventing the output stage from presenting too much of a transient, there's a 33 ohm resistor permanently across the secondary of the output transformer. So we will not be, when we turn the speaker off, we will still hear sound in the speaker, and we will still have some impedance, but there is a difference in the impedance when you turn the speaker on. It's the difference between the 8 ohm speaker that's here and the 33 ohm here. So basically, when the speaker is turned on, you get probably about 7 ohms across the output transformer. So let's look at what the impedance analyzer shows. Well, my goodness, that doesn't look good, does it? The reason is that the resistor is incorrect for this output transformer. It has a lot more impedance in the primary because it's designed to match an output tube. And if you watched my other video on this, you know that generally output tubes need somewhere between 2 and 10K of impedance to work into to get a good match. You notice that it starts at 2K and goes up and then falls off drastically with frequency, but what's all this other stuff about? Well, this, I think, is it's a good feature, but I think it's also misleading. It says here, resistor too high, and down here it says resistor too low. But then it has a question mark, and I think the reason it has the question mark is that, frankly, I don't think the impedance analyzer knows whether the resistor is too high or too low. It just knows that it's not getting good readings. So let's change the resistor to 100 ohms, and I'll do that on the actual circuit as well, and rerun it. Now what I've done is I've changed to a frequency from 20 hertz to 100 kilohertz. Okay, that looks a lot better. So what's going on here? Well, one of the things that you need to pay attention to is when it gives those red arrows, or those looks like a picket fence or a serrated edge there with a red warning label. All that really means is the resistor isn't right. Don't depend on whether it says it's too low or too high, because obviously if it was too high here and too low out here, there's no way you could get in between, so you couldn't fix that, and yet we did. So how did we fix it? Well, we just raised the resistor value to 100 ohms, and it fixed both. So I think putting the resistor too high or resistor too low on there is misleading, and I suggest that that Digilant change that to perhaps resistor too high or low, or resistor not correct, or something like that, because it's misleading. If you read too high and you lower the resistance, sometimes it doesn't work, sometimes it does. Similarly, when it says resistor too low, sometimes if you raise the resistance it fixes it, sometimes it doesn't. Basically, if you get those red warning signs, just try a different value for a resistor. Now, one thing that I've also changed is the from load first to resistor first. So you might ask why I did that. Well, what I was trying to do is to see whether it made much of a difference. So remember what this curve looks like. Basically, it starts at around 2.5K. It goes up to a maximum of about 10K, around a kilohertz, and then it falls off dramatically. So based on this, you would say, well, this speaker, this particular unit is not going to work very well in a hi-fi amplifier. It just doesn't have the high frequency response that you need. I'm going to now turn off the speaker and rerun the analysis. Remember now, this is with a 33 ohm resistance on the output. Starts out at 2K, about the same as before. And now you see we start getting those errors that it says resistor too high, resistor too low. Let's go to a 1K here. And try that. And I haven't tried this before. Okay, now you see it works. So what we've done is, by removing the speaker impedance, we have increased the impedance at the output, and therefore the reflected impedance is different. Now notice that it goes from 2.5K, where it originally was, which is basically a characteristic of the transformer, and goes to a high of nearly, well, certainly more than 60. It looks like about 75 kilo ohms at this same point, which is probably at or near the resonant point of the transformer itself. So we've learned two things. One is, as the load on the output goes up, the reflected impedance, or as the impedance of the load on the output goes up, the reflected impedance also goes up, which is what we would expect. So now, just for those of you that might be curious, well, okay, why did you change to resistor first? Well, frankly, I was just experimenting. So let's go back to load first and run the same thing again. As you can see, I've gone back to load first, which was the configuration that we used throughout part 1, and the configuration we used initially on this one. And so let's look at what the results are. Well, it looks like it's almost exactly the same as we got with resistor first. That is, it starts out at around 2.5K, goes up to about 75K at a frequency a little below a kilohertz, and then falls off dramatically at higher frequencies. Now, in terms of actual audio frequency, one reason I'm using 100 kilohertz is just to show you what happens at the very high frequencies. We could only go to 20 kilohertz here, and we'll run that and see what it looks like. This is, of course, the normal audio range. Okay, now let's go back to the 100 ohm resistor that did not work in the resistor first case and run that. Once again, starts at 2.5K, runs up, and says the resistor is wrong. So what we've learned, I think, is that the warnings on the resistor are good. the text that says that it's too high or too low is misleading. Don't pay attention to that, in my opinion. Just ignore the text. And notice where you have the little picket fence indicator, that means the resistor is wrong. You might have to go up, you might have to go down. And I know that Craig Hollabaugh in his video was having trouble with the same thing. I have not found any sort of way to relate the text to what is going wrong. I have found that in general, if you know you're dealing with a higher impedance circuit, like an output transformer compared to a power transformer, then you're probably going to need a higher resistance. Okay, let's go to $1K. And run that, and then I want to show you a few more things before we finish. And okay, and we're getting what we expect. Let's now run this with the speaker turned on. And by the way, the reason that you hear a sound even with the speaker turned off is basically there is feed through the 33 ohm resistor into the speaker. So basically the 33 ohm resistor is in series with the speaker in one position and in parallel with it in the other. Okay, here you see that we have a relatively flat 2 to 3K out to a little past a kilohertz with the speaker connected, maybe 2 kilohertz. Then you get a peak that peaks to about 8,000 ohms at about 5,000 hertz, 5 kilohertz, and then is back to the 2.5 kilohertz just before at about 9 kilohertz. So what you have here is a decent radio speaker, which is what this unit was designed to do. It's a signal tracer for tracing radios of the 1940s and 50s. So this is a perfectly adequate output transformer where the maximum frequency response of a radio was around 5 kilohertz, which would be about here. And if we only run out to 5 kilohertz, you'll see that we get a fairly well-behaved response. But radios, of course, AM radios of the day weren't designed to work out in high fidelity. Now I would like to show you a couple of other things that I think may not be quite correct. I've already showed you the meter and analyzer. Let me show you the decibel plot. Now the decibel plot looks fine, and you notice that over here the decibels are shown, but it still shows ohms. Now I'm going to turn the ohms off, and you notice it still shows decibels. Now I'm going to turn ohms on, turn decibels off, and back on. And notice it shows decibels even though it's ohms is still shown. I would have expected that since we're just dealing with impedance here, that this would make a difference. Now you'll notice there that it reads decibels. That is, decibel is still turned on, but we're actually reading impedance in ohms. The same thing is true of when you use Siemens. Now Siemens is of course admittance, and notice that it turns on the primary admittance, that is the G sub P and the B sub P, the admittance and susceptance, I never can say that word, which is fine, except ohm is still shown here. I would have thought that these would be like radio buttons where if you push one, the other one turns off. Same thing is true when you do Henry. You notice now it says Henry over here, but Siemens and ohm are still on. When you click farad, it just adds that to the list and so on. So I think those are just some little glitches that whoever did the user interface on this probably needs to look at, because it's probably a better idea if you just have one of these highlighted based on what the display is actually doing. Now you can also turn on dissipation, and you notice down here you get a curve that shows the dissipation, and then you can do quality and you get a quality curve. But now notice that I can turn on phase, I can turn on decibels, and then I'm just going to click on dissipation, and you see all of them are on, and yet what it's showing is dissipation and decibels. These are the typical little glitches that occur in a new piece of software, and I'm sure Digilant will fix all of these. I am overall very happy with the Impedance Analyzer. I'm going to be doing a lot of work with it. Unfortunately, I'm not going to have a lot of time for a while, but maybe later this year or early next year I'll be able to get back to some of this and do some real work. But I am happy to see that there are other people like Craig Hollabaugh who are picking up some of this stuff, and perhaps they can carry it through for the remainder of this year. At any rate, I do promise to finish that workbench, that radio workbench, before I get consumed by the busyness of the fall. But I hope you've enjoyed the videos, and I hope that you'll have a nice day.